Hey students, welcome to class. This is Mrs. Brunk. Thanks for joining me for Geometry B and Module 19.1, which is nets for three-dimensional figures and cross-sections. So our learning goal today is going to be able to describe the 3D shape formed by what's called a net and to describe a cross-section. So when we first started studying these three-dimensional figures, and I was showing you some of the models in my classroom, we had the clear acrylic kind of, exteriors, and then I would pull out these colored, foldable things in the center, and I laid them out, and I showed you what they looked like if we laid them flat. Well, what that is a net, and that actually shows the two-dimensional material slice and what it's shaped like that it would take so that we could fold it up and create a three-dimensional figure. So that's what a net is. So a net is a diagram of the surface of a three-dimensional figure that can be folded to form a 3D figure. So it's a diagram of a three-dimensional figure, but made in 2 dimensions with a little bit of thickness so that we could fold that and create a three-dimensional figure out of it. So to identify the 3D figure from a net, look at the number of faces and the shape of each face. So now remember, we have looked at 2 base shapes. Those are called the prisms or the cylinders. We looked at 1 base shapes that had a special point called the vertex, and those were pyramids and cones. And then we had the 1 shape we've looked at that has no bases, and that's the sphere. So we're going to first take a look at prisms. So you see here some real common prisms, ones that we've been looking at. There's the triangular prism, and if I identified the base, sorry about my dog snoring, but if I identify the base, there's 2 of them. There's 1 there. There's 1 down here, right? Okay. We have the cube. So a cube has 2 bases. Actually, really, no matter what face you're sitting a cube on, it's going to be a base. So there's the top and the bottom, right? So we got these 2 faces. There's the rectangular prism or the box. There's the bases right here. And so on. And if you were to take and unfold this, those faces, because you can tell in the prism themselves, they don't intersect, they're parallel, they would actually have to be on opposite sides of a big, long kind of rectangular shape that's split up into several pieces that would actually create what's called the lateral surface. So out here, this part's called the lateral surface. And if you can imagine, here's a really good example of this, like if you've ever taken a label off a can, I know that's a cylinder, but a cylinder is still a prism, and you laid that label out flat, it would turn into just a big rectangle that could just wrap right back around that can and cover it, like, say, a soup can label. And that's the lateral surface. So if you look at the lateral surface of, say, this triangular prism, you can see that if we laid it out, we'd make 1 big long rectangle that's split up into 3 separate regions. And that's actually what this is showing. So this is showing me my lateral surface out here, right? This is lateral. This is the sides. And essentially, if I were to fold along those edges there, I could create the sides of that prism. And then I would just take the 1 base up here, base 1, and then this down here, base 2, I would just fold them along those edges, and it would just kind of serve as the top of that surface that wrapped around, and then the bottom, B2, would be the bottom. So this is a net for a triangular prism. Okay, so again, kind of characteristic of these prisms is you'll see these bases on either side. So we've got right here on either side of 1 big rectangle that actually is split up into smaller pieces that will wrap around the figure. Now there's lots of different ways to make a cube, but this is one of the really common ways to make a cube. We've got 6 congruent squares, but 4 of them have to lie in one long rectangle, because again, that's going to kind of, if we were to fold the top up here, or fold it down, and then the bottom up right here, made it so they were parallel, then we could just wrap around those sides and create an enclosed figure. Okay, so this is my base 1, and this is a base 2. Okay, you can do the same thing with the rectangular. So this is a net for the rectangular prism, and there's the bases, right? And then the lateral surface is this right here. This is my lateral surface that'll wrap around. And again, it's split up into 4 smaller sections, 1 to wrap around each side of that rectangle. The pentagonal prism. So we've got a pentagonal prism. So we've got the pentagon top right here, right? And the pentagon bottom. And when I take and imagine kind of folding this down flat, I'll have my 2 bases on either side. It's like almost like I'm taking a can off a soup can, or taking the top off, and on the top and the bottom. And then when I'm just kind of folding it back away, right? Now they're pointing away from each other. They would eventually, if I put this back into a 3D shape, be parallel to each other. And then, of course, we have the lateral surface here. It's just going to wrap around the sides. Okay, and then close that figure. Okay, so we could actually put a volume in. So that's how you can always identify a net of a prism, is you'll have this lateral surface that's one big long rectangle, and you'll have 2 congruent bases, 1 on either side. Okay, so again, here's this lateral surface. It's like one big rectangle when we lay it down, but maybe it's folded along these little edges, because say these were where each of the corners of that prism were, right? So that's a hexagonal prism. And again, how we name these figures is we say what type of base it is, and then what type of 3-dimensional figure it is. So in this case, I have a hexagonal prism, but let's say instead I only had 1 base, and then all the points converge to another point called the vertex, then that would be different, right? So these are typical ways to create a net for a prism. You got your 2 bases that end up being the top and the bottom, or the front and the back of the figure. Now, typically when you see a net for a pyramid, it's oftentimes drawn like these down here, right? Where it's almost like sort of a, I don't know, I guess a banana is not a very good example here, but where you're basically taking the pyramid and maybe in through the vertex here, kind of reaching in there, and then just kind of peeling down, taking this part, peeling it down, taking this side, peeling it down, taking the other back side and peeling it down. And all of a sudden, we have a shape that kind of maybe looks like a star, a flower, or something like that. But this right here is the base, right? And then I just peel down a triangle off either side. And when I lay it flat, that's what the net looks like, okay? And so you basically have like, these 3 petals off the side. Whereas if I had a square or a rectangular pyramid, then when I folded down those sides, right? So this side's coming down, it's going to go back this way. This one back there is going to lay down. This one over here is going to lay down. This one on the front is going to lie down. And we'll end up getting something that looks just a little bit different than that last one, because again, I still have 1 base. There it is. But now I have 4 lateral faces. So that's what this is called, is a lateral or side face. So then here's a typical pentagonal pyramid, a hexagonal pyramid, or maybe even a little more complicated rectangular pyramid. I think the prettiest looking one, the more sides the base has. So again, here, and this is hexagonal. So 1, 2, 3, 4, 5, 6. And you can see here in the center of this little star, 1, 2, 3, 4, 5, 6. So that's what a net for a pyramid of some type is going to look like. So you've got, these side or lateral faces that kind of converge up to that point that's just called the vertex, right? And now if instead we went backwards and we just took those lateral faces, those triangles, and peeled them back down, we get this little like flower shape. Now the final kind of net we're going to look at is in terms of the one base shapes. It's going to be the cone. I don't know if you've ever made a cone before, but I remember doing that. Actually, we probably called it a dunce hat, but anyway, I've made a cone more as a hat before. And basically, when you think of making a cone or a cylinder or a sphere, one thing that you know for sure is that part of your drawing is going to be circular, because a cylinder has a circular base, a cone has a circular base, okay, and the sphere, its essential slice out of it is a circle. So different ways that, again, where that cylinder could kind of be drawn, but I do know I have that one big long rectangle piece, which is again like almost like the soup label on a can. And then I got these two bases, base 1 and base 2. Okay, so base 1, base 2. So then, of course, the three 3D shapes that have circle as the basis of the shape itself would be the one with the two bases, that's the cylinder, the cone with the one, and then the sphere, which has like the great circle in the center. And then the rest of it is the lateral surface. That's what a net for a cone would look like. Okay, kind of imagine taking a piece of cardboard or something and rolling it up into like a little megaphone thing, but that's what we could make a 3D shape out of. So when we identify the 3D shapes that are formed by a net, the first thing that we do is we identify what the bases or what the bases are. Well, this thing clearly has bases, 2 of them, and so I can tell that it's going to have to be some sort of prism. So that's base 1 and base 2, the opposite sides of the figure, and I can just see folding along those edges, wrap around after I fold the top and the bottom up, and would create this little prism. So this is what a typical prism looks like. You've got this one big long lateral surface, just split up into smaller rectangles or squares. When we look at a pyramid, so a pyramid, again, you can kind of think about the sides being sort of like part of like a banana of some sort, and then you just kind of fold it and peel down the sides, see what's left over. So this one is a square. This would identify the base, so square. Pyramid. It's got just the one base. Where this one would make, and again, we name it by what is the face of the base or the bases. These are regular pentagons. So we could say that penta would be a pentagonal pyramid. So C would, of course, then be a triangular prism. So we can tell that if that's kind of sitting there as the base, the other sides are going to fold right up. They're all going to meet at the exact same point here, here, and here. And you all of a sudden have yourself a 3-dimensional figure. Now with a sphere, which is what this next, or not sphere, but cone, this next one. You can kind of imagine it's got like a circle that's kind of stuck to the lateral edge. That lateral edge has got it right all the way around it. So it's processed. It takes a little longer. So this one here is going to be, we've got that base, which is a circle. And you can kind of imagine kind of just folding that up and kind of wrapping around that base. And so I would get a circular pyramid, which is also called a cone. And this would be a triangular pyramid. Okay, so looking at the next example, we have the two circle bases. So here's base 1, here's base 2, and then this is the piece right here that's just going to wrap right around and enclose that figure. So again, this is a cylinder, a net for a cylinder. So on this one, I see those triangular faces that, just are like basically this pyramid folded down, right? And there's the base. So here's the base. And then eventually you can identify what type it is by looking at these lateral faces as it's laying flat, right? So we've got a 6-sided base. And in this situation, I have a base that's a hexagon, so I would say a hexagonal. But this time it's a pyramid. One base, and all the lateral faces, when they fold down, become triangles. Next, we have a cube or a square pyramid. Oops, I'm sorry, prism. But I see those bases on opposite sides of that lateral surface. It's the top and then the bottom. And that's also what I see here in this example. So we've got these congruent triangles. You can imagine kind of folding them along the edge, laying them parallel to each other, and then just kind of wrapping around the lateral surface. So that would be a triangular prism. Now, the final thing we're going to look at in today's lesson are cross sections of figures. So essentially, you want to be able to kind of imagine if you were to take and draw cut out a slice of this figure, say parallel to the base. What exactly would that shape look like? And then also, what then has that done now to, as far as calculating the... So again, really a cross section is just a slice out of a three-dimensional figure. And really the shape of what that cross section is dependent on really the angle that whatever you're slicing it with. You can kind of imagine like a flat plane, like a slice out of space, which is a plane, right? If you can imagine it kind of just shearing through the three-dimensional figure. And depending on the angle that it cuts at, it'll make different shapes. So, for instance, in this cylinder, this plane cut through, and it cut through parallel to the bases. And because it cut through parallel to the two bases, it actually is going to create a shape that is exactly the same circle, in this case, as the top and the bottom, or the bases, right? It's congruent. This little thing right here, this little slice, is a circle, and it's congruent to the bases. Oops, exact same size. That's, remember the symbol we use for congruent? So congruent to the bases. Okay. So now if instead, let's say, it had kind of gone through at an angle. Say this plane started up here like this, and then it was kind of coming through, and it kind of came out down here instead. Then it would create a shape that's like this. And that actually, so again, if this is sort of like a, you can imagine a 3D or a 2D, two-dimensional, like a plane or whatever, kind of cutting through like that, right? If it was coming through at an angle there, then that shape right there is actually called an ellipse. So let's see, that would be an ellipse. Or you might think of it as an oval. Or let's say it kind of cut down here towards the bottom of the base like that, and it kind of went in through like that. It might hit this side right here. Oops, right there, and then maybe a point here on the back side and here like that, and then it might create something like that. So that would be like a parabola. So really depending on what angle it's coming in through the figure, the cross section could be different shapes, okay? So like for instance in B, if I wanted to describe this cross section, I mean, you might look at that and say it's a square, and that is true. It looks like it's a square, and that's because you can tell that the base is a square, or maybe it's a rectangle that's got really close dimensions, but regardless, so it's congruent to the base, or I'm sorry, not congruent to the base, it's similar to the base, so it's just a much smaller square. And because that's a pyramid and all those points are kind of converging towards that vertex, the closer the cross section would get up here to the vertex, the smaller that square would get. But as long as it's parallel to the base, it's still going to be a square. So this is a square, but instead of being congruent to the base, it's going to be a square that's similar. Remember, that means similar. S-I-M-I-L. Similar to the base. Okay. Now again, if you went in at different angles, say you were going to cut through and you hit with the plane, say up high, like here in this one, but then it went down at an angle, so now it's kind of coming out down here. So if that were the case, then it would just make some other sort of, well, it would still in this case make, a quadrilateral, but it would just be some different kind of quadrilateral than a square. It's not going to be similar to the base, but it's going to be still a four-sided figure, okay? So really it just depends on, you're just really honestly just looking to see what the shape that's shaded in to, like functionally to do these problems. That's really all you're trying to do, but just to kind of imagine other types of cross sections, you could just kind of think of tilting that plane back or forth, and is just whatever shape would be formed by that then. Okay. Now, if you took a cone and you sliced it with a plane, say parallel to the base, now that would be like going this way. Of course, you would get a circle like you would with that cylinder, but because the one that they've drawn here is going right through the vertex here. See how it's right up here at the vertex, and then it's hitting the base here and here. Oops, not here and here. Here and here. It's actually creating a triangle. So it's some sort of triangle, creating a triangle. And actually, depending on the angle, it's actually creating an isosceles triangle. Right, so isosceles triangle, meaning, it's got those two equal sides. Here we have a cylinder, and instead of going between the two bases, parallel to the two bases, this time it's going through the lateral sides, right? And you can see that it's creating a rectangle. So it's just creating a rectangle. Okay. And again, you get different shapes based on which angle, whether you're going through the sides, going parallel to the bases, whatever, you'll get different shapes. So really just looking for whatever's highlighted there in the drawing. Here we have a square prism, and of course it looks like it's hard to draw, but it looks like they did the plane section going parallel to the bases. So this would be a square. We're assuming it's a square that is congruent to the bases. So it's important when we're kind of describing it, if we can be specific like this, like saying that it's congruent to something or similar to something, then we should include that, okay? But otherwise, if that's unclear, then we just indicate the shape like we did with isosceles triangle or rectangle. Okay, this triangular prism, so again, if they had gone through this way like that through the bases, or parallel to the two bases, we would have gotten a triangle. But instead they're cutting from base to base, and so they're just getting a little rectangle here. And the closer to the top of that section up here, like closer to this piece, the smaller that rectangle would get. But what I can see right now is a rectangle. was a rectangular cross section. In G, it looks like they went from corner to corner in a cube, and they were able to create a triangle, but specifically this one's an equilateral triangle. And the reason why this one's equilateral triangle is because we know that cubes, all faces are the same, and so these sides of this triangle are the diagonals of those congruent faces, those squares, and so those diagonals are all the exact same length, so that's equilateral triangle, all three sides equal. Remember, this side and this side and this side are equal. And the final cross-section, a cross-section out of a sphere. So we talked a little bit about one special cross-section out of a sphere, and that's the one like if you were to slice right through the center, including that center point, which would be called a great circle. And that means that's the biggest circle you can get out of a sphere. And but in this case, this is tilted somewhat, right? And so that cross-section, and it's also towards the top there, right? That's a much smaller circle. So that would just be called a small circle for obvious reasons instead of a great circle. Okay. So that does it today for today's lesson. We just really wanted to give you kind of a look at what are some, special features about nets, how you can tell what the figure will be from a net of the figure, and then also just a little bit about cross sections. So thanks for coming to class.